Good morning. My name is Vladimír Kučera, and I'm going to talk about the results of the Department of Platforms. In fact, I am the only reporter for that department here, and the subject of my presentation will be the publication, Decoupling Periodic Systems and Algebraic Approach, which was published in the IEEE Transactions and Automatic Control, and the research was funded by the RoboProx project. So I titled the presentation Discrete Time Control of Periodic Systems. Periodic systems abound in nature. For example, because of the rotation of the Earth. Periodic control is well known to humanity since time immemorial. For example, in the ancient Egyptian agriculture, they knew that crop cycling increases the yield. Modern applications include industry process control, robotics, communications, economics, time series analysis, many other areas. Periodicity is typically induced if the inputs and outputs are sampled with different rates. Then the system period which occurs is the least common multiple of the rates. Mathematically, linear periodic discrete time system is described by these equations where T is the discrete time, 1, 2, 3, 4, 5, and so on. X is the state of the system, U is the input, Y is the output. They are all vectors of appropriate sizes, and A, B, C, D are matrices, time-dependent but periodic, which means that they are the same after some period of time denoted capital T. In time-invariant systems, we introduce transfer functions to study their properties. In periodic systems, we introduce the so-called periodic transfer operator. It's well known that the output of the system can be expressed in terms of the Markov parameters. Of course, they are time varying and periodic here. When we introduced one step ahead shift operator, zeta, as shown here, then the input and output of the periodic systems are related by the so-called periodic transfer operator, denoted P here, and it is a function of two variables, zeta and, of course, the time. And it is periodic. So the goal of my presentation is to show that discrete time periodic systems can be treated as time invariant systems, however, of a higher order with a special structure. So to do this, we cycle the signals. The operation of cycling is based on the idea that the samples within one period are stacked together in a vector. And then the system matrices are the same. So we create a large vector which is of size T times period times larger than the actual signal. And in this way, we have a unique non-zero subvector at each point, which cyclically shifts along the column blocks like this. Then, of course, the system matrices have a very special structure due to this shifting. The B matrix looks like that. The A matrix has the same structure. And what's important that the eigenvalues of this shifted time invariant matrix are determined by the teeth root of the eigenvalues of the original system defined by the transition matrix over one period, which is the same there. Okay? And therefore, the periodic system is stable if and only if the cyclic representation, time invariant one, is also stable. The output matrices are diagonal, and now this idea can be used, of course, in control applications. The cyclic representation of the periodic system is time invariant, while having t times, capital T, times larger the dimension than the original system. The control system analysis and synthesis can be done using standard techniques for time invariant systems. But thanks to this peculiar structure, though the system matrices are larger, the computational burden is much reduced. I use this approach to solve the problems of model matching and system decoupling for periodic systems. So using this cyclic representation, we obtain time invariant matrices denoted by overbar. And the key point during the control synthesis is to ensure that the calculated time invariant matrices have that particular diagonal structure so that they can be indeed considered to be a cyclic representation of the original system. So, specifically for decoupling. Decoupling a time invariant system means achieving a diagonal transfer function using feedback. Decoupling a periodic system, logically, means achieving a diagonal periodic transfer operator for all times using the periodic feedback. A time invariant system can be decoupled if and only if its transfer function has a certain diagonal Hermite form. A periodic system can be decoupled using periodic feedback if and only if the transfer matrix of the cyclic representation has a multi-diagonal Hermite form. So what the Hermite form means? If the single box represents a transfer matrix, then using certain operations from the right with this matrix, we can make it lower triangular. For periodic systems formulated as cycling matrices, the period, for example, t equals 3, leads to 3 times 3 matrix, t times larger than the original one, and each block must be made triangular so that we keep that specific structure. And if these blocks, instead of triangular, are in fact diagonal, then the system can be decoupled. So we have a blue diagonal in the single box. For the period t equals 3, we have 3 diagonals. It's a multi-diagonal system, and the diagonals are broken red, blue, green, as shown here. Just an unusual and interesting recent publication which I found in the literature. Periodic control is here used for underwater exploration of fish in the patrolic domain, and the control aims to coordinate and synchronize the behavior of a shoal of 3 fish robots. These robots aim to survey a submerged area cyclically with many points of interest. I find it interesting. Thank you very much for your attention.
I'm Tilman Becker, I'm the director of Ricaip, and I would like to steal 5 minutes of your time to give an update on what Ricaip is doing. And as you know, it's one of these strategic programs that have started in 2016, but we're on extending it even longer. First of all, the EU project itself will be extended until the end of August. That was the result of successful negotiations with the EU Commission. And we are currently in the process of setting up a legal entity to keep the Ricaip structure together with the joint test beds in Brno and also in Germany to continue. There are two research issues that we are focusing at the end of the project. One is the use case of distributed production, which is really unique. Most other research groups are not focusing on the bigger picture, combining production at different distributed places. So we're all about connecting the test beds and have a controlled execution of the manufacturing that is distributed over multiple sites. So we're working on the interfaces, the data models, and the connection of different sites to the joint distributed system. And then in the second use case, lift this up one level, getting into the realm of more AI and business engineering to see different sites as service providers and see how service combination, service retrieval, and so on can be worked on. As I said, it's a big infrastructure, so it provides backbone for research, 32 publications from the team. It's also very important for outreach, to get connected to others, be visible. So we had 30 visits in the Ricaip Testbed Prague in the last year, and there are more to come. A lot of those are very high-level meetings and visits that are important for political and societal outreach. And we're also working on these social aspects by providing seminars and workshops on these issues. And you see on the right a number of projects that are to one kind or another rely on the infrastructure that Ricaip is providing. So this is really an important backbone structure. And in terms of outreach, we're really short about this. We go to the big engineering fair. I was at Hanover in spring last year myself on DFKI's booth. We were invited as a guest. That was very helpful because these infrastructures are big, complicated, and expensive. And we were part of a very big booth united by innovation with many, mainly industrial partners on the Brno Engineering Fair, which is a really impressive one that almost compares with Hanover, not exactly in size, but in terms of participants, in particular exhibitors. So the last word will be save the date, please. In the beginning of June, we'll have an official final event of the Ricaip project, mind you. That is sort of the first event of the Ricaip Center, which will be the name for these activities in the future. That's an event for outreach to industry, policymakers, researchers, and basically all stakeholders. It should be European-wide, and you'll see invited lectures that might be interesting to all of you, workshops on specific topics, and live demonstrators of the activities, in particular the use cases I mentioned at the beginning. So, thank you. If there are no questions, I would lead over to Pavel Burget, the leader of the testbed here, to say more.
Hello, good morning also from my side. I will give a short overview of the results of testbed here in Prague, which is part of the Ricaip, and among other things we are responsible for the distributed production use case, as Tilman mentioned. Here you can see a list of papers. The first three are conference papers, the rest are journal papers, or one conference paper that were submitted, but we don't know about the results, or we are going to resubmit in case of rejection. So testbed is not only the infrastructure, but we been building also the research team so that the results can be combined. And of course, we are open and already in cooperation with other departments here in CIRC. Regarding the application areas and prototypes that were created, I would like to emphasize the area of simulations using the NVIDIA Omniverse environment, which is provided by NVIDIA and which invests into it massively. And you can see from the pictures here that there are various fields of interest here, like the robotic manipulation, robotics and vision in terms of robot manipulation. We've been also dealing with multiphysics simulations related to additive manufacturing. Another project is about mobile robotics. And then you can see some examples of finished application in terms of functional samples or prototypes that were developed for the companies whose logos can be seen in the bottom. So that's for the overview from my side. Now I give the floor to my colleague Varun, who will present two papers.
Thank you, everyone. My name is Varun, and I will be presenting our work, comparative evaluation of 3D reconstruction for object pose estimation. It was a work done with collaboration with Dr. Torsten Sattler and our former colleague, Asia. I want to start with a small motivation. As Testbed, we are mostly interested in practical applicability of our research. So for today's topic, we will be mostly focusing on robotic manipulation. And one of the key to solve robotic manipulation is 6D pose estimation. We started our research by, so current state of the art, how object pose estimation method works by finding a test image and some form of representation of object. It can be a CAD model or something similar. So we start asking a question, can we replace such CAD model, which is generated by state-of-the-art hardware, which the process is quite expensive and time-consuming. Can we just replace it by just capturing set of multi-view RGB images? So hence we started to do large-scale experimentation and evaluation on the 3D reconstruction method, which will evaluate how well they perform in terms of 6D pose estimation of an object. So as you can see, we used like one of the most used data set, which is called YCBV dataset, which consists of test images and the ground truth annotation of 6D pose. There are 21 objects. I use most of the state-of-the-art reconstruction method, both learning and non-learning based methods. Then two top-performing pose estimation method, mega pose and the foundation pose. So the pipeline was pretty straightforward. To reconstruct an object, we need to get a multi-view images. We leveraged a robotic arm, did a 360 view of an object, capture more than 300 images of object around it using a RGB camera. Did the 3D reconstruction from various methods, post-process it, and replace this CAD model. Replace this mesh model with the CAD model. So when we did this large-scale experimentation, we found very interesting results. First, in terms of accuracy, how well are the 3D reconstructed mesh model in terms of the mesh model generated from the state-of-the-art hardware, which you can see on the left side. We saw that there is in order to get the accuracy and completeness of a mesh, there is a threshold of 1 centimeter. In the middle, what you see is like various reconstruction method and their pose estimation result. On the solid line, you see one of the best pose estimator method called foundation pose, and the dotted is like mega pose. What we found here, like the reconstructed mesh, when replaced instead of CAD model, there is a large gap in between how the 6D pose estimation of object performs with this reconstructed mesh. Also, we found that the runtime of this mesh, especially the meshes which perform the best in terms of object pose estimate, takes almost more than 6 hours or 8 hours, which is not very practical in terms of real-time robotic application. As a conclusion, what we found, even more interesting results, that the 6D pose estimation of object relates more towards the how the texture of a mesh looks like rather than the 3D reconstruction. We also found, you can see on the lower left that the PSNR is almost directly proportional to the average recall of the object pose estimate. In the middle, we also found that sometimes even when the mesh is not properly reconstructed, it actually still performs very good in terms of object pose estimation, unless the texture generated by this mesh are pretty good enough. On the right, these are one of the hardest objects, which are very hard in terms of object reconstruction, are the small, shiny, non-textureless object, where most of the algorithms struggle to do the 3D reconstruction, and the pose estimates are much worse than the other. So that concludes my first paper, and the second paper is OPFormer, Object Pose Estimation Leveraging Foundation Models. It was done with colleagues from Testbed. So inspired from our previous research and the benchmark for object pose estimation challenge, which consists of object onboarding. So let's consider a task where you don't have any representation of object, how fast you can get the object on board. Second is object detection, and third is 6D pose estimation. We wanted to make such a modular pipeline which can accomplish all this task under, let's say, 5 minutes, which can be applicable in the real robotics. So hence we started to make a modular pipeline, how we can tackle this task. Most of our innovation lies in whole pipeline, especially in terms of how we process the CAD model. So we start by object onboarding. Let's say if the object CAD model is not available, we use the nerve-based method to 3D reconstruct the object and create a database of such objects. So once given a test image, we start by using the object detector, which gives us the bounding box of an object, and this bounding box of an object is sent to our model. So comparing to the other state-of-the-art method, we start leveraging the state-of-the-art foundation model, which is a Dino V2 that time. We intelligently use our weight adapter to get the information from every single layer, try to condense it, and try to efficiently process every single layer, information from low-level semantics to high-level semantics, and send it to our encoder and decoder-based transformer-based method, where each templates in encoder model, in encoder model, like the model try to learn the relationship between the inter-templates, which actually helps them to learn how the symmetry and other properties of mesh or objects works better. The key innovation here is like how we intelligently push our NOCs-based template into this encoder model using the rope encoder. Then this is passed towards the decoder model, where like most of the filtering happens. So it gives us the estimate of the best pose estimate, best meshed template related to the test image, which is sent back to our output module, which does basically PNP and find the final pose of an object. So these are some ablation studies which actually shows like how we become best state-of-the-art method in terms of industrial, household, and every single kind of data set. Yeah, so here are some of the visualization. What you see in this image is like how does the on the top left you see the test image, how it looks like, and in the middle there is a contour of our detection pipeline, how it estimates the 6D pose, and on the bottom left, it's just the segmentation of each object. Does the animation work? Yeah, so you can see like how actually it's look in 3D. So what you see here, like the green meshes are the ground truth where object is actually really located in the space. And on the pink is the rough estimated. This whole process is just using a single RGB image. It's a bit far away from what you expect for the robotic manipulation, but we are very close in terms of state-of-the-art methods. In terms of results, when this method was released, we were the state of the art comparing to all the methods in terms of benchmark for object pose estimation challenge. We were the only method which can run under almost less than a second and perform state of the art results in almost all the given data sets altogether. Yeah, that's conclude my talk. Thank you for your attention.